Okay, yeah. Thank you for the invitation. I'm really excited to be here and talk about this work. And thank you for the introduction, Sontara. So, as you said, I'll be talking about our work that was titled "Solving Allen-Cahn and Cahn-Hilliard Equations Using the Adaptive Physics-Informed Neural Networks." And this was work done by myself and my collaborator, Dr. Jia Zhao at Utah State University. Okay. To talk a little bit more about my background and my interests. As some stated, my background is in computational mathematics and industrial mathematics, which I studied at Utah State University. But during that time, I really had a broad interest in the areas of data science and machine learning. And we were really excited when I was a master's student when PINNS came out and the potential that they had and kind of the unification of these different interesting fields. So currently, I'm a data scientist in AI at PNNL. And when I say AI, I typically mean so deep learning here. In this case, a lot of the work I do is in applying different types of and principles from deep learning to solve problems that are of interest at the lab. So some of the areas that I am interested in personally are the robustness, interpretability, right, and safety of these machine learning systems, in particular deep learning systems. And I do a lot in the area of computer vision. And I've been able to apply some of the things I've learned working with PINNS and in other areas to areas in material science and engineering, as well as control at the lab. And I'm looking forward to seeing where else, right, we can apply them. So quick overview of the talk is basically what I'm going to talk about is some of the techniques that we developed to utilize PINNS for solving these phase field equations, in particular, the Allen-Cahn and the Cahn-Hilliard equations. So throughout this talk, I'll walk through some of the things that motivated these techniques and what we did to kind of solve some of these things we saw, especially with the perspective of these phase field equations. So I'll start by talking a little bit more about phase field models and PINNS, and then we'll talk about the methods and the results later. So phase field models have applications in a number of different areas, including image analysis, material science, engineering, fluid mechanics, and even the life sciences. And so we'll focus on these two fundamental models here, the Allen-Cahn and Cahn-Hilliard equation. So these equations are reaction diffusion equations, and they model interfacial or multi-phase problems. And they can be quite difficult to solve numerically due to their sharp and moving interfaces, to name one reason. And there is a field of work, right, devoted to just solving and working with these equations numerically. We'll note that these are gradient flow systems, and they can be derived from a free energy function, which many well-known PDEs turn out to be these types of special cases. So the image on the right here shows solution of the Allen-Cahn equation in 2 dimensions at a few different time steps. So the way I like to think about this equation simply is the separation of, say, oil and water when you kind of mix it up. So here we can see these 2 different concentrations at 1 and -1 with these interfaces between them. And these move over time and can be quite difficult to resolve. So a little bit more on these equations, right? They're related in that they both can be derived from this Ginsburg-Landau free energy function at the top here. So the Allen-Cahn equation, we can derive by taking the L2 gradient flow, and we can obtain this form with this equation here in the middle. And the Cahn-Hilliard equation, we can derive by taking the H inverse gradient flow, seen here at the bottom. And so when we start this study, we'll work with these equations, right, in the simple 1D case with the initial conditions shown here with periodic boundary constraints. And then we'll work on solving harder and harder problems and move into the 2 and 3D case once we've kind of developed some of these methods. So I don't think I need to say much here about PINNS to the group. Other than that, right? We were quite excited when they first came out back in, I believe 2017 was when the first manuscript came out. And I know they've grown in popularity and have been applied in a lot of different areas since then. But in our work, the code provided here at this GitHub repository was quite useful. The TensorFlow implementation was nice and straightforward. And so, being a data scientist, we also have a big focus, right, on loss functions and how do we optimize these problems to find suitable solutions. So I did want to focus a little bit on the loss for PINNS. And I'm sure, again, you're all familiar with this. Here, the loss function is this mean squared error, which has these 3 components. One focuses on enforcing the initial conditions. The next focuses on the boundary constraints. And finally, the third focuses on this residual F network. And a lot of the methods that we developed are simply choosing how to sample these collocation points for this residual F network, along with some other tricks that we found useful when working with phase-filled equations. Okay, so next I'll move on to some of the methods that we developed here. We'll start with adding weights to the loss function and talk about mini batching, and then some of these adaptive sampling techniques that we found useful. So here we started by trying to solve this 1D Allen-Cahn equation with the gamma 1 parameter of 10 to the negative 4 and the gamma 2 parameter of 5. And we found that simply our naive attempt of simply kind of taking the approach to solve these equations that was demonstrated on Schrodinger's and Berger's equation, we were unable to get a good solution here. So we took 10,000 static collocation points and used full batch optimization methods. And if we look at the solution on the right here for you, we can kind of see what is being learned. And then we can also look at the error in that network and see where our error is the highest. And then we can look at different time steps to see what's being learned there. And we see that it's kind of just this flat line. And maybe the first thing to point out is that even this initial condition at time t equals 0 is not being learned well. So this kind of motivates the first technique that we used, which was adding weights to the loss function. So going back to phase-filled equations, these equations are dissipative and they're not reversible. So intuitively, we would think that if the solution isn't learned well at t equals 0 or some initial time, it probably won't be learned well after that. At least that's the intuition, right? And we found that in general, the PINNS did kind of follow that same thought process or that same rule, right? We found that if a solution wasn't learned well, that error kind of propagated out through time. So the first thing we proposed to solve this issue was to emphasize the importance that the initial condition is first learned well, and we simply added this constant to this term in the loss, so C0 here at the bottom. So and here's what happens when we did that. So when we added a constant C0 equals 100, we find that the solution was now being learned well at that initial condition, And it was doing better across some parts of the domain, but there were other parts of the domain that still we were having a hard time learning, right? And with these phase field equations, this hard transition from -1 to 1, it wasn't getting quite all the way up there to 1. So in order to further improve this solution, we came up with this sampling in space strategy. So again, looking at kind of the intuition behind phase field equations, which have these sharp interfaces that move over time, we thought that sampling in these areas might aid in the solution. And this wasn't necessarily anything new, right? Adaptive mesh refinement methods have been used in classical numerical analysis for a while. But we were able to kind of lean on some of these techniques to help solve these problems. And one of the other things we found that, right, the error in the residual F network was related to the error in this U network. So we could use that as a surrogate for how to find where our solution is not being learned well. So the algorithm we proposed went like this. So we started by training the network for say an iteration, and then you can assess the error in this F network at test points and randomly sampled across the domain. And then you can determine which points had the highest error there, and we could take a portion of those points and add those to the original collocation points, and then train the network, and this could be repeated at different steps. So here's a visualization of what this method kind of looked like. So again, these blue points on the left represent the static collocation points that were sampled across the entire domain of the problem. And then the points in red represent the resampled points that were obtained by finding where the highest error was in the F network. And the idea here was that these blue collocation points kind of helped to enforce that the solution was still learned well across the entire domain, while these adaptive points allowed us to focus more on different areas at different iterations that were not being learned well.
Colby, I missed the previous slide. You choose the red points based on the residual.
Correct.
The value of so you threshold at some point the residual, right? And
right. So we say, so let's take, say, a bunch of Latin hypercube sampled points across the domain, pass those through the network, and look at, say, the top 200 points of highest error.
Yeah. So in the DeepXD paper in CREV, we call that RAR, refinement adaptive.
Right.
Yeah. So I was wondering if it's the same thing or different way to sample.
Right. Yeah. I have seen that since.
Yeah. Okay. Please proceed.
Okay. So that was kind of the idea for sampling in space. And then
Colby, this is Varun. I had a question regarding the previous slide. I'm from Brown.
Yeah.
So at what point do you stop and collect measure the error? Do you wait for it to converge, or how do you know this is where I need to measure my error?
Yeah. I believe what we typically did was just after every iteration of the atom optimizer, we just assessed it there and added the points, and then did that after each iteration.
Okay, thanks.
Can I ask a follow-up question related? This is Yan Jung from Brown. I'm wondering, have you considered removing the existing random collocation point and to add your resampled point? Because by your keep adding resampled points, it seems to me that the number of points you need to train on it would increase later on.
Yeah.
So that in that perspective, my first thought was all right, if you resample certain points, then you may get rid of some existing points, so that making your number of the collocation points remains reasonable. So have you tried doing this, or do you see any issues on implementing it?
No, and in fact, that is actually what we did. Excuse me if it wasn't clear here, but yes, these red points change every iteration, and we remove them, just like you said.
Oh, I see. Thank you.
The only points that are remaining are these kind of static collocation points, the blue points.
Oh, I see. Got it. Thank you.
Yes, definitely. Okay, yeah, thank you for the questions and clarifications. So another technique, right, that's common in machine learning is mini batching. And this has been shown to help to avoid less desirable local minima when compared to, say, full batch gradient descent. Right, and I'm sure everybody's familiar with this, right? Instead of taking taking all of the data and calculating the gradient there, you take a subset of the data and go in that direction. So this was another technique we proposed to kind of help to find optimal solutions here. So what we would do was, when we were first running the atom optimizer, we would do this in mini batches before using the LBFGS optimizer. So here are some of the solutions when we applied these different techniques. So in the table here at the bottom, we can see just kind of the naive implementation of the base pins, or I believe that this might be referred to as vanilla pins now. And then what happens when we add weights to the loss, and then when we combine those with either mini batching or space sampling, we saw that both, in this case, both mini batching or space sampling provided good solutions. So in this case, maybe slightly better with the space sampling technique, which helped us define these better solutions. So we then took these approaches and tried to solve the Allen-Cahn equation, still in 1D, but with more difficult initial conditions. And we also looked at varying this gamma 2 parameter. And this gamma 2 parameter has to do with how sharp the transition interfaces in the problem. So we found that with smaller gamma 2 parameters, we were able to solve the problem with this initial condition. But with larger parameters at say 3 and 4, we were unable to get the solution to converge, even with trying these sampling in space approaches. And we found that for when gamma equals 4, the error occurred early on at t equals 2.5, and then again propagated throughout the solution. So this is where we developed sampling strategies that were adaptive in time as well. So we saw that space sampling helped you solve the problem when we had these moving interfaces with these phase field problems. But we
Colby, can you go back? Can you go back one slide here? So Yonjon, who asked the question earlier, maybe he can answer this question. But
yeah,
it looks like it's not just a resolution, but with Yonjon and Lulu, I think, we wrote a paper on dying ReLU neural networks, and they look like that. So here, of course, Yonjon, don't you think it's in other words, do you actually need new points for resolution, or we need a better way, like a different activation function or adaptive activation function without actually introducing new points. That could because it looks like our our paper where we try to approximate. So half of the function would be approximate, the other half would be like that, sort of the average.
I think
so I'm asking you, John.
Yeah, I think that is related, George. I think because if you add a point that was previously unactivated location, that would help. Is it making sense? So that your training data.
No, that's what I'm saying. So it's really, that's what I'm saying. So the introduction of new points actually helps his mini batch.
Right.
Not the resolution, not from the approximation point of view. He has enough points.
Right.
So even if you have to jiggle around the points that he has without, but that's so I think that's something that we all get confused. That it's not really we're helping the optimizer. That's what I'm saying here.
Yeah, I agree with George.
It's not an approximation issue.
Yeah, what activation function did you use for this?
I believe we were using the at the end hyperbolic tangents with the ReLUs.
I see. I think this is related to what George pointed out.
Right.
Yeah.
And we did see during this, there was some work on those adaptive activations, right? And it would be interesting to see how those worked here. Definitely.
Yeah, ours is with the ReLU, but maybe John, you can put on the chat the paper so Colby can see it, that you can see some similarities.
Yeah, sure.
I appreciate that. Okay. Yeah, I appreciate that discussion. So one approach, again, that we took was kind of thinking about the, from the perspective of phase field equations and their time dependence. We went into more sampling and strategically placing these collocation points. So we actually came up with two methods for kind of implementing this adaptive approach in time idea. And one is simply selecting where we're sampling the collocation points from. And the next, we use actually two separate networks at different time intervals. So this is the main idea behind what we call time adaptive approach one, where, as I said, we are just restricting where we're allowed to pull the collocation points from. So we focus all the collocation points on some restricted domain from t equals 0 to delta t. And then as the solution is learned well in this restricted domain, we go on to say delta 2 or a larger slice of the domain until the solution is learned well across this entire domain. And we can still perform the space sampling approach here in this restricted domain if we're having trouble solving the problem in the smaller domain. And now what we call time adaptive approach 2, we actually learned separate networks for each different time intervals. So we would learn this solution well here on, say, time t equals 0 to 0.1. And then when we had the solution learned well there, we can move on to our next time segment and use the learned solution from the network 1 as kind of initial conditions to start off network 2. And we could do this until we had networks that covered the entire domain of interest.
Can I ask a quick question here?
Yeah.
So when you use the previous value as an initial data for training the next, for example, your network 1 at time 0.1 value should be matched to the network 2 at that same location 0.1.
Right.
But if you use the same initial data, then you are basically using the data, the value at time 0 in network 1 So don't you need to flip your parameter to match the discontinuity might occurs? I think that's something you can do by easily flipping your signs, so that just you can change the time sign to be minus, then you can start to match your discontinuity. I mean, you start with the continuity part somehow. I think you get my point, right?
Right. No, that's a really good point, and I wonder, why we didn't think of that. And right, sometimes we find that time adaptive approach 1 worked and time adaptive 2 approach worked well. And one of the factors in deciding which one to use was, right, if the solution isn't learned well in network 1, you kind of propagate that error throughout the rest of the networks, and there are potentially discontinuities.
I see. Yeah. So I think it is an easy fixer. I think you can just check your code, just changing the sign for T part only, then see how it turns out. Yeah, just one comment. Yeah, thank you.
Cool. No, thank you. Okay, and finally, when we moved on from trying to solve Allen-Cahn Cahn-Hilliard equation, we used this final technique, which was using an intermediate network for working with these higher order equations, right? Because backpropagation, in the case of Cahn-Hilliard, this 4th order equation, it starts to become quite expensive to calculate. And we also found that we were having a hard time solving this problem. So what we did was introduce a second network to reduce the need to calculate higher order derivatives. And we found that this, right, improved computational efficiency and accuracy. And I believe since we've done this, there are, right, methods for dealing with these as well. We ended up finding that to work well. So now, after talking about some of these tips and tricks that we found useful for working with these equations, I'll show some results for solving both the Allen-Cahn and Cahn-Hilliard equation. So moving back to this Allen-Cahn equation with that second initial condition that was more difficult to solve, we found that using this time adaptive approach led to good solution here. And we found that time adaptive approach 1 worked well, but we were still getting slight differences at the end here around x equals 0 that we were having a hard time resolving. So next, we moved on to the 2D and 3D cases of the equation, and we used this form of the Allen-Cahn equation. So this was kind of the classical shrinking up of the droplet problem for the Allen-Cahn equation, starting with this kind of initial droplet, which as time goes on shrinks with this equation through time. And we can look at the bottom row, the images on the bottom row, which are the error in this solution. And we can also move on to the 3-dimensional case, which is, again, similar. We can model this droplet shrinking over time with the error rates on the bottom row here. And finally, looking at more complex domains, we saw the Allen-Cahn equation in this L-shaped domain using both a mixture of space sampling and time sampling techniques. So that we moved on to this, in some cases, more difficult Cahn-Hilliard equation. So we started by solving it in the 1D case, where gamma 1 equals 10 to the negative 6 and gamma 2 equals 0.01. And we found that, again, with this combination of space and time sampling, in this case, time adaptive approach 1, we were able to solve this kind of toy problem here with an error of 9.5 e negative 3. And then looking at the 2D case where we have these two droplets that come together over time, we were able to model that as well. And so, right, in conclusion, we were able to find that we could kind of leverage PINNS to solve phase field equations. And we were able to kind of use techniques that were inspired by classical numerical approaches and approaches from deep learning. And one of the techniques we used here was loss function weighting. And some of the main methods were, again, these adaptive sampling in time and space. So kind of directions to go, since we've done this work, is right, the data-driven discovery of phase field models. And I'll mention that my collaborators at Utah State University are actively working on this direction. And another thing that could be useful if these methods were found useful would be to add adaptive interval lengths for the time sampling, right? Because as you start to split up the problem into time domains, it can become more computationally expensive, right? But there might be ways to selectively or adaptively change the lengths of the different intervals depending on how difficult those intervals are to solve. And then, right, the final point here is that there's a lot of work being done with PINNS, right, and a lot of different methods, and it'd be interesting to incorporate some of the methods that we worked on here with some of the other advancements, and we've touched on some of those already, including this deep XDE network and the methods they use in this library. So I would like to acknowledge the sponsors for this work, the National Science Foundation, National Institutes of Health, as well as NVIDIA Incorporation for providing computing resources, and the University of Utah HPC Center that we also were able to borrow some compute time from. So with that, I'll show some of the references in this talk, and thank you for your time. And I'd be happy to talk about any other questions or discussions.
Thank you, Colby. We have questions for the speaker.
I have a question, please. Please, can you tell us what activation function do you use, please? Can you hear me?
Yes, yes.
Yeah, what activation function do you use?
Yeah, I believe we were using the ReLUs and hyperbolic tangent activation functions.
Okay, okay. Thank you.
Maybe not ReLUs, Colby.
Yeah,
I'll differentiate. Yeah,
I think you're right. I think we tried those at one point and we were getting very poor solutions. Typically, the hyperbolic tangents work better in this case.
I think Matthias had the question, right? Matthias, I saw you raise your hand or not? Or just say hi.
Oh, in fact, it was both. So first, I wanted to say thank you for this impressive talk. But in fact, I also have a question. For me, the most impressive picture that you have shown was the one with a calculation or simulation on this L-shaped domain. Yes, this one, slide 29. I mean, this is really, from the mathematical point, really challenging because you have a very strong singularity. Can you somehow comment how you solve this problem? I mean, what boundary conditions you imposed in these corner points?
So here, in general, we use the homogeneous Neumann boundary conditions. And so we found that adding a larger weight to the initial condition on the loss function of 1000 worked in this case. And we used the network with 6 hidden layers and 120 nodes per layer. And did that, maybe I'm not answering your question. And
I think maybe if I should say, maybe the solution has no singularity, so the geometry does not it does not affect the geometry that much. I mean, usually for L-shaped domains, because of the singularity at the corner, if you take a certain right-hand side, you should see this behavior. But I think your solution is smooth enough.
Oh, okay.
Colby, what would be interesting, I don't know if you have it in the paper, for example, in a problem like this, to show the distribution of the points that you are discovering through this continuous adaptive method. So we'll see where the points are concentrating, if indeed they do a refinement of the singularity, for example, if there is a singularity. So I think that would be something that people would be looking at.
Yes, that's true.
Yeah, I appreciate that.
Minlang, do you have any question? Minlang, do you have any question? Minlang in my group worked on Cahn-Hilliard for inverse problems, so he had some success, but also some. Minlang, do you have any questions for Colby?
Not now, but I just have, yeah, I actually have one quick question. So how do you do with like, did you introduce a second network to apply?
Yeah, that was not clear, Colby.
Yeah.
If you have a plot or something to show us how you introduce the intermediate network to compute the derivatives.
Or because I found that it was really hard to like compute the fourth order derivative if you just use one network. So that's my question.
Right. Yeah. And I agree. Even reading the paper, maybe it wasn't entirely clear. And right at the time, maybe I thought it was clear. But here, I have this hidden slide here. If you can see that talks about, okay, so here we have this. We introduced this mu network, right? And then we define f as, right, u sub t, and then mu sub xx. And then the way we define the loss on f kind of looks like this for the Cahn-Hilliard equation. Does that give a little more help? I'm sure, right? Something like a diagram would be a lot more useful.
Yeah, that's all I was curious. Yeah, thank you.
I have a small question. This is Dr. Abdul Khalid from MTSU. Thank you for interesting talk. Do you learn gamma 2 using PINN?
So the focus of this work was the forward solution. Though the lab, or right, my collaborators are working on that inverse problem of learning those parameters with data.
So in the nonlinearity, if you do not have the coefficients, did you try to use PINN to learn these parameters and then solve using the adaptive collocation network you have? Did you try that, or you just assume those variables?
We assumed these variables.
I see. Yep. Okay. All right. Thank you.
Do we have more questions? So in case we don't have more questions, thank you, Colby, for joining us, and thank you for the talk.
Thank you very much.
We'll move on to our next speaker. Okay. Yeah, Vivek. So our next speaker is Vivek Oomen from the Crunch group. Vivek, you may want to share your screen and just see if it works.
Yes, I'm not able to share my screen.
I made you the co-host just now.
I'll try once again. Yes. Yes. Yeah.
Okay. Yeah. So a quick introduction about him. We all know him. He is a first-year PhD candidate at the Crunch Group, and he would be presenting to us a paper review on learning mappings from iced airfoils to aerodynamic coefficients using a deep operator network. Thank you, and you may begin.
Yes, thank you, Somnata. I hope you're able to see my screen in the presentation form.
Yes. Yes.
Yes, so today I'm doing a paper review of learning mappings from iced airfoils to aerodynamic coefficients using DeepONet by the following authors. So a brief outline. I will quickly go through the motivation and the related works. I'll explain in detail the methodology used, then briefly go through the data set they have used. Then we'll have a detailed discussion on the results, then the conclusions and discussions. So this is my plan for today's presentation. Coming to the motivation. So we know when the altitude increases, the temperature decreases by lapse rate of usually 6 to 8 degrees Celsius per kilometer of height, minus 6 to 8 degrees Celsius per kilometer of height. So that is represented by this curve. As the altitude increases from 0, we see the temperature is decreasing. And usually the airplanes fly in this range of 9 to 12 kilometers altitude. If you look at how the atmospheric pressure varies with altitude, we see at the altitudes where airplanes fly, the atmospheric pressure is usually close to 150 to 200 millimeters of mercury in that unit, in that relative unit. So if we go through the phase diagram of ice, water, and vapor, we see at 150 to 200 millimeters of mercury pressure, the freezing point of water does not vary much. So the point is, for the aircrafts that fly at an altitude of 9 to 12 kilometers, the freezing point of water is still close to 0 degrees Celsius, but the ambient temperature is close to minus 50 to minus 60 degrees Celsius. Because of this, ice accretion or ice deposition starts happening on various parts of the airplane. So this is an image where the wings of the airplane are subjected to ice accretion. This also happens to the engine. So this can decrease the performance, etc. So if you see here, you see due to ice accretion, the profile of the various components which are specifically designed for maximizing lift or minimizing drag has been drastically changed. So this has a great impact. So this is why researchers have started studying
this is a great movie. Where is it real or is it fake? Is it a simulation?
It is an animation, Professor. I got it from this link, YouTube. It is just a 35-second animation.
I was wondering, how can they make it real? Okay, it looks so real.
Yes, Professor, yes. So the motivation is ice accretion leads to reduction in lift, increase in drag, and reduction in engine efficiency. So common methods to study ice accretion. So initially, in earlier times, people used to conduct experiments in icing wind tunnel or icing wind tunnel tests. But the problem here is it's very expensive to perform this experiment. So recently, people have turned to using computational fluid dynamics simulations, CFD simulations, for achieving this task. Related works. In 1958, Dr. Gray performed experiments on NACA 65A004 airfoil. And these are a few images I took from his paper. They saw that there is a reduction in lift, increase in drag due to ice accretion, as expected. Their other related works include Rajkumar et al. Used one hidden layer neural network to predict aerodynamic coefficients as function of angle of attack and Mach number. Then there has been works where airfoil geometry was represented using the signed distance function, and the CNN was used to predict the aerodynamic coefficients. And there are works where neural network was used to directly learn the relationship between ice shapes and aerodynamic performances. But the problem here is that when you use ordinary neural networks or CNNs, the generalization was very poor. That is where the DeepONet comes in. So the DeepONet introduced by Lulu and al. Was based on the theorem proposed by Chen and Chen in the 90s. So according to this theorem, it's the universal operator approximation theorem that states a mapping from an operators, which is a mapping from an input function space to an output function space, can be approximated in the following manner. Suppose u of, if there is an operator that is transforming the input function u to an output function g of u, it can be approximated using in this format. So it is an inner product between g of u, which represents the branch network output, and f of y, which represents the trunk network output. And if you take the inner product, it shows that the error in prediction will be bounded by epsilon. So here, the input function space stands for the airfoil geometry and iced airfoil geometries, and the output function is the space of different aerodynamic coefficients, which is a function of the angle of attacks alpha. So in this work, they have used this DeepNet architecture. For the branch net, they are using a convolutional neural network, and that takes iced airfoil images as the input. The trunk net takes the angle of attack alpha as the input. The output of branch network and the output of trunk network are subjected to an inner product, and then a bias is added, and they predict multiple functions. So the coefficient of drag as a function of alpha, which is the input to the trunk net, the coefficient of lift as a function of alpha, which is the input to the trunk angle of attack. So this is what they're doing. Now, coming into the how they implemented this. So here we see the same DeepNet is used for predicting two functions, CD and CL, coefficient of drag and coefficient of lift. So let E be the output of the branch net, which takes the image nu as the input, and F be the output of the trunk net T that takes angle of attack alpha as the input. First, they transform E and F in the following matrices. So ME corresponds to M number of.
Vivek, just one second. How do they parameterize the shapes? I guess they have the real image through CNN, right?
Yes, they are using images. I will be explaining it here.
Okay.
200 by 200 images. Yes, Professor.
Yeah.
Correct. So we will be transforming the output E in the following manner. So here it represents an M times P matrix. It stands for M different vectors of P dimensions, or M P-dimensional vectors. In this case, M stands for the number of functions they are trying to predict. And if you see here, there are two functions, CD as a function of alpha and CL as a function of alpha. Because of this, M is equal to 2. So ME consists of two P-dimensional functions, and MF, which is the output of trunk net, is represented as two P-dimensional vectors. Yeah. Now we perform an inner product operation on each of these so that the dimension of P is reduced. So if you see here, we do the inner product, and to each of these functions, we add the bias. So this is what is done here, this term. Now we compute the loss as the mean, create a loss defined as the mean square error between the true coefficients, true functions, and the predicted function. C label stands for the true functions of CD and CL. And they are using Adam optimizer to minimize the mean square error with respect to θ1, the branch network weights, θ2, the trunk network weights, and B, the biases that is added after the inner product operation. As a representation metric to evaluate the performance, they are using this term R square, which is 1 minus the mean square error between the predicted and the true functions by variance of the true functions. And they call this R square term as accuracy in the remaining part of the paper. So for creating data set, so here they are using only one airfoil profile, which is NACA 0012 profile. And they are subjected to different ice accretion. So the different profiles represents the different shapes of the icing in this region. So this is one of the samples of computational mesh on one of the sample ice profile of NACA 0012 profile. So here is the data set they used. They did the simulations and created the following data set. So they used 10,000 different airfoil profiles of NACA 0012, but with different ice profiles. And each of them, they performed a simulation and computed the coefficient of drag as a function of alpha. The same they did for coefficient of lift as a function of alpha. For test, they considered different 367 airfoil profiles, again, which is just NACA 0012, but they have this unseen ice profiles, icing profiles. So the overall profiles will be different. So again, they calculate the CD, they compute the CD and CL. So this represents the test data set. Regarding the data set, the airfoil images are of the shape 200 by 200 by 1, and they are normalized between 0 and 1. The angle of attack varies between -20 to +20 degrees at an interval of 20 degrees. So there are a total of 21 different angles of attacks. So angle of attack is also normalized between -1 to 1. The output to be predicted are two functions: CD as a function of alpha, the coefficient of drag, and CL as a function of alpha, the coefficient of lift. So if you see the number of training samples, you have 9,999 different unique air profiles because of different icing patterns, and each of them subjected to 21 angle of attacks. Similarly, for test, there are 367 times 21 test samples. In the paper, they have said for the generating data, they have considered Mach number equal to 0.44, but they haven't mentioned what Reynolds number they have used. Regarding the deponent, this is the same figure. The trunk net they are using for the first experiment consists of one input neuron, then 2 layers with 40 neurons each. So the latent dimension of the deponent will be 40. And the Adam optimizer with a learning rate of 10⁻³ is used. Batch size is 64, and they were able to train the model with just 100 epochs. They haven't mentioned the activation function they have used. And for robustness, I think they trained with 10 different random weight initializations, trainable weight initializations. So this is the first experiment they performed, in which they tried to predict CD and CL as a function of alpha using the deponent mentioned in this slide. So here we see the average training accuracy. So the left column represents the training results, the right column represents the test results. So in the train results, this figure corresponds to the coefficient of drag performance. So this airfoil numbers, again, they are just nominal numbers. I'm sorry. Yeah, these numbers, these just represent different ice profiles. And this we see that on train data, the coefficient of drag is predicted with good accuracy, with the minimum accuracy being just around 97.2. And similarly for coefficient of lift also, on training data set, they have good results between 95.5 to 100% accuracy. This R square is the accuracy. Then for test data set, for coefficient of drag, the performance is good, like it varies from 97 to 100, but for predicting the average test accuracy for coefficient of lift, there is one sample whose accuracy is close to 86.4%. So they check what happened with that particular sample or that particular case. So this is the airfoil icing profile of the 168 sample, which is this outlier kind of thing. And we see that the truth, which is the red line, is not very well in agreement. The predictions obtained by the deponent is not in good alignment with the true predictions. So here there is a difference. So they tried to analyze why is the reason, and they saw that for most of the training data sets, the coefficient of lift, the problematic situation, was usually in this range. And we see that they show that from this figure, the 168 iced airfoil is kind of outlier. But that's it. They just showed this and they said this is why it is not performing well. So that's what the authors have shown. Next, they go into the experiment involving deponent, in which they compare the deponent with CNN. So here, the CNN architecture used is shown below. It's shown here. The iced airfoil images are fed as input to a usual CNN, and the output layer is flattened and is split into two parts. So the first part represents the drag coefficient, and the second part of the flattened layer represents the lift coefficients. So one problem one of the disadvantages compared with DeepOnet is in DeepOnet we can predict for any value of alpha, but here alpha has to be set as a hyperparameter. It has to be fixed during the training of the model. So we fix the resolution of alpha for the prediction of drag coefficient and lift coefficient, and they do the prediction. Here they have shown the variation of the loss convergence plot has been shown here. But so we see at the beginning, DeepOnet has a much lower loss compared to the CNN, but I'm not able to see clearly what happens here because it was not in the log scale plot. But the good thing we can see is it has both CNN and DeepOnet models have converged with just 100 epochs. So here they present the results. They compare the train and test performance of the DeepOnet, which is blue in color, with the train and test performance of the CNN, which is yellow or orange in color, for prediction of coefficient of drag and prediction of coefficient of lift. They are varying the number of convolution layers used in the branch net of the DeepOnet and the number of convolution layers in the CNN model. So in both cases, we see the training and test accuracy both performs better for DeepOnet compared to CNN. But one thing I would like to point out is, I think this is not a fair comparison because DeepOnet has an additional trunk net. So if you are keeping the branch net, if you are matching the number of training parameters, trainable variables in DeepOnet is much greater than that in the CNN used. So, yep, that's one point I want to note. Next, they perform an experiment to understand the effect of number of hidden layers in the trunk net. So before I explain, I want to mention that to understand these results, according to the authors, the trunk net has an input layer, it has an output layer, and it has hidden layer. So if hidden layer equal to 0, it means there is no, it has just the input and the output layer, that's it. So we see on increasing the number of hidden layers, initially the accuracy increases in prediction of drag coefficient and prediction of lift coefficient, and then it saturates close to 3 or 2. Yeah, so this is their observation. And in this case, number of hidden layer neurons is fixed to 40 neurons. Next, they perform an experiment to understand the effect of number of hidden layer neurons in the trunk net. So here they vary the number of hidden layer neurons from 2 to 320. And we see initially the model predictions improve and then it saturates out. Here also the output layer neurons, which is the latent dimension, is fixed to the latent dimension of the DeepOnet, or the output layer number of neurons in the output layer is fixed to 40. In the next experiment, they try to understand the effect of the latent dimension of the DeepOnet. So they vary the number of neurons in the output layer of the trunk nets. And we see, so here there is a sharp increase in performance on increasing the latent dimension of the DeepOnet. And this is expected because now it has better representation capacity, since more basis functions are used for making the prediction or for predicting the coefficient of drag and coefficient of lift. So the number of hidden layer neurons are fixed to 40. So these are the conclusions presented by the authors. DeepOnet generalizes better than the CNN. The trunk network has this architecture, which is input layer, output layer with 40 or latent dimension, one hidden layer with 40 neurons. The branch network with 3 convolution layers performed best. And the number of neurons in the last layer, which is the latent dimension, had a greater impact than the number of layers in the previous, number of neurons in the previous layers. That was not provided. Then while comparing CNN and DeepOnet, the authors could have fixed the number of trainable parameters so that there will be a fair comparison, because DeepOnet has another network called the trunk network, which has its own trainable parameters. Plus, they just forgot to mention the Reynolds number and the activation. That's all. So thank you. Questions, answers, suggestions. That's it. Thank you.
So we have questions for Vivek.
Thanks, Vivek. This was very comprehensive. Are there experimental data? Do you know if people have real data, not simulated data? Do they mention any references?
In one of the references, let me just go there. Yes, for the work done by Rajkumar et al., it's a 2002 work, I guess. They have used both numerical and wind tunnel data. That's what they said in the references. So I didn't go through that, but yeah, they have mentioned like that.
Do we have questions for Vivek? So if we don't have questions, thank you, Vivek, for the presentation. And with that, we come to an end to our weekly seminar this week.